Hi, welcome back to another lesson. In our last lesson, we dealt with linear expansivity, but in this lesson, we're going to start with area and volume thermal expansion. That said, let's get started. This solid has three unique characteristics. It has an area and it has a volume. In our last lesson, we saw linear expansivity, which relates much more to length and breadth, but in this lesson, we'll see area. We'll relate linear expansivity, thermal expansion, to area and volumes. Now, if we know that from our basic elementary arithmetics that L1 times B1, that is the length times breadth of any object, is equals to area. Now let's call the initial length of this object L1 and the initial breadth B1. So to give us the initial area of the surface A1, so that A2, which is the final length and the final breadth after it is heated, let's call that be a product of L2 and what? And B2. So that if L2 is the same thing as L1 into 1 plus linear expansivity times change in temperature from our last lesson, obviously B2 will be the same thing as B1 into 1 plus alpha, and so that my area, you know that our area A2, which is the final area, is L2 times B2. That will be the same thing as L1 into 1 plus alpha delta theta dot L2 into 1 plus alpha delta theta. So that this is now the same thing as L1, this is B, this is the breadth for B2. So that is L1 B1 into 1 plus alpha delta theta all squared. So expanding this becomes A1 into 1 plus, if you expand this, it will give you 2 alpha delta theta plus delta theta times alpha all squared. As usual, we know that alpha are always given in terms of very small figures. Alpha, our linear expansivity could be something like 1.2 times 10 raised to the power minus 6. And by the time you are squaring this, it will lead to an extremely small figure. So alpha all squared always tends to what? To 0. So that the whole of alpha delta theta all squared will tend to 0. So that A2, finally, A2 is the same thing as A1 into 1 plus 2 alpha delta theta. Now from here, we know that 2 alpha delta theta is a constant. We can now interpret this and represent it with the area expansivity, so that we can conclude that the area expansivity of the object beta is the same thing as 2 alpha. So that A2 conclusively will be the same thing as A1 into 1 plus beta delta theta. Same way, if you are looking for volume expansivity, you will know that the volume expansivity of that object will be 3 alpha, because, and so that V2 in volume expansivity is the same thing as V1 into 1 plus volume expansivity times delta theta. Now, so you can see the relationship between volume expansivity, linear expansivity. While this is linear expansivity, my area expansivity beta is the same thing as 2 of the linear expansivity, and your volume expansivity is the same thing as 3 times the linear expansivity. Now let's see some questions to help us understand it better. Now our first question says that the iron has an edge 15, an iron cube has an edge 15 centimeters long. Now since this is an iron cube, obviously L1 is equals to 15 centimeters long, and because it's a cube, my B1, the breadth, is equals to L1, which is also equals to 15 centimeters. And my change in temperature, it says we should look for the new surface of the question says we should look for the new surface area of a phase when the temperature rises to 80 degrees Celsius. So that my change in temperature is equals to my final temperature 80 minus the initial temperature, which is equals to 60 degrees Celsius. Now, to calculate the area expansivity, we already have that the linear expansivity of this object is 1.2 times 10 raised to the power minus 5, so that the area expansivity of this object will be 2 of alpha, which is 2 times 1.2 times 10 raised to the power minus 5. That's equals to 2.4 times 10 raised to the power minus 5 per Kelvin. So that my final area of this object will be given as A1 into 1 plus beta change in temperature, which is equals to A1 that will be 15 times 15. 15 times 15 into 1 plus beta is 2.4 times 10 raised to the power minus 5 times 60. So that is equals to 225 into, if you sum the whole of this up, you should come up with 1.00144. Now, so that this is equals to 225 times 1.0.144 should come up to 225.3 centimeter squared. So this is going to be my new area. Our volume expansivity is given as 3 times the linear expansivity. That's equals to 3 into the linear expansivity of 1.2 times 10 raised to the power minus 5. That's equals to 3.6 times 10 raised to the power minus 5. And since it's a cube, my length is equals to 15 centimeters. My V1 will be equals to 15 times 15 times 15, which is equals to 3.375 centimeter squared. So that V2 will be equals to V1 into 1 plus the volume expansivity times change in theta. That's equals to 3.375 into 1 plus 3.6 times 10 raised to the power minus 5 into change in temperature of 60. So that the final answer, V2, will be equals to 3382.29